Gnanam paramam dheyam. Knowledge is supreme.
Here is another application which is very useful. Let us look at what is called a quadratic curve. A expression of this form, ax square plus bxy plus cy square plus dx plus 2ey. So, what does it look like? It is a polynomial in sort of x and y, right, but the highest power it is 2. So, it is called a quadratic curve. The idea is, if you try to plot x and y in the plane, it will give you some points, right. Look at x and y such that they satisfy this equation. For example, let us look at some special examples. What is the equation of a circle? X square plus y square equal to some r square, that is a quadratic curve where some of these coefficients are 0. A parabola, y square equal to ax, right, or a hyperbola, or your ellipse, x square over a square minus y square over b square equal to 1, say, right. All are quadratic curves, right. All conic sections come as quadratic curves. So, the question is, if you are given like this, how do I visualize this? What is this curve? I want to visualize this curve, right. So, there are two simplifications one can do. One can try, supposing your equation is such that the terms x y, right, and that is ey and x y and exy, sorry, product terms and x y terms are 0. Supposing your equation looks like this, okay. That means this b is 0, then d is 0 and e is 0. Supposing it is a special type of, okay, then that form is called canonical form of the quadratic form. So, first step is how to bring a general equation of a quadratic curve to canonical form. Can we give some method of transforming, because then it looks slightly simpler to handle, okay, and that is done by shift of origin. If we just shift the origin, let us do that process, okay. So, it is easier to sketch and understand if the curve is given in the canonical form, okay. So, we will see how it is done, okay. So, this is a quadratic, we want to transform this to this form, right. So, to do that, what we do is we shift the origin. How do you shift the origin? Earlier origin is somewhere, you translate, right, you translate it. So, what is the shift of origin is done as follows. You write x is equal to x tilde plus some x 0 and y tilde as y tilde plus x 0. That means what? You are defining a new variable x tilde and y tilde, where what is x tilde? It is x minus x 0 and y is equal to y tilde is y minus y 0. You are shifting, right. Every point is shifted by x 0 y 0. So, what is the aim of doing this? That means, if I put these values in this equation, those terms which I want to make 0, they should vanish, right. That is the criteria. By this substitution, I want to choose x 0 y 0 in such a way that when I put those values in the equation, the terms of x y, x and y, they vanish. So, let us put that condition. So, put these values in the given equation. So, that is the equation ax square plus 2bxy plus c, right, that is equal to 0, that is the original one, in terms of x tilde and y tilde. So, once you just simplify, it becomes ax tilde square plus 2b tilde b x tilde y tilde plus this is equal to 0. So, what do we want now? In this transformed equation, I do not want the d to appear, right, I do not want e to appear, right. This I want them to be equal to, I want them 0, that means what, this is d tilde, this is e tilde, I want them to be equal to 0. So, let us see what is our conditions that puts on x 0 and y 0. So, compute all these three quantities in terms of x 0 and y 0 in terms of the original E, F and D, right. Those are already given to us, the equation. So, this equation A, B, C, D, E, F all are given to us. Our aim is to find x 0, y 0 such that those terms vanish, right. So, that these terms vanish. So, we have found those values in terms of x 0, y 0, E and F. So, what is required? This should be equal to 0, this should be equal to 0 and this should be equal to 0. So, let us put those values. So, it says for d tilde and e tilde to be 0, there is the value of d tilde in the previous one, that is the value of d tilde, right, and that is the value of e tilde. So, that should be equal to 0. So, that x 0, y 0 are given to us, right. Sorry, x 0, y 0 is to be found, A, B, C, D, E, they are all given to us. What is it? This is a system of equations, two equations in two variables, so which we want to solve. Okay. So, if you want to solve that, when is this system solvable? And we want a unique solution, right, we want only one. So, what is the two equations and two variables, what is the condition? The determinant should not be equal to 0, right. Is it clear? Go back 2 by 2, right, determinant should not be equal to 0, rank should be full. So, AC minus B square, right, that will be a determinant of that matrix, Ax is equal to, right, that should not be 0. So, that should not be equal to 0. So, they will have a unique solution in that case, right. 2 by 2 determinant matrix should not be equal to determinant of the coefficient matrix should not be 0. So, you get in this form. So, if it is not 0, then you will find a unique solution, take that choice of x 0, y 0, your equation becomes of this form, right, it becomes to canonical form. So, that is normally we have been doing it in our school also, whenever you want to solve some problem in coordinate geometry or geometry, right, you say let us assume the origin is here, that is very common. Why is that done? Because something becomes simpler, some things vanish, right, computations are simpler. So, this is the first thing what Wedner does is that by shift of origin you can bring your quadratic curve to canonical form. Okay. So, that is your x 0 delta, so and f is given by this. So, what is the advantage of canonical form? X square plus y square equal to something, right, that is canonical form of a curve. What is the advantage? There is symmetry here. If we change x to minus x and y to minus y, the curve remains the same, right. What about ellipse? That also has the same property. So, canonical forms have central symmetry also. So, that is one advantage. So, now let us look at, so what we will do is, we will assume you have got already shifted the origin and you have got a quadratic curve which is in that form, ax square plus 2bxy plus cy square equal to some constant h. Such things are normally called quadratic forms. So, canonical form of a quadratic curve is given a name, right, all such expressions are called quadratic form. Okay. Just to say that you are in the canonical form. The claim is that given the quadratic form, there exists an orthogonal matrix P and scalars lambda 1 and lambda 2 such that this equation in a new variable looks like lambda 1 x dash square plus lambda 2 y dash square equal to h, where is x dash y dash, that is related to the old variable x y by that matrix P. So, the change of variable what you am doing, x y is the original variable, right. So, what we are doing is you can find a matrix P which is a orthogonal matrix and define new variables as x dash y dash by multiplying x y by P. In that variable, this equation looks like this only, right. So, now let us try to understand geometry of this, what we are doing. You are given a ax square plus 2 bxy cy square, that is some kind of a curve. What does changing the variable by orthogonal means? What is the orthogonal transformation, say in R2? What are orthogonal transformations in R2? Determinant equal to 1, right. Orthogonal means P transpose P is equal to identity. So, determinant is plus minus 1, right. Basically, these are all rotations. Orthogonal means they are all rotations only, okay, or reflection against a line through the origin. So, what does a rotation do? So, to the normal coordinate axis, what will it change it to? If I am applying a change of variable in the plane, a point x y goes to x dash y dash where P is orthogonal. So, the original, if two lines are perpendicular passing through the origin, say the coordinate axis, what will happen to them? Will only be rotating, right. They will go to some other two orthogonal lines, right. So, this means what? This means that by a rotation you can change your coordinate axis to the original coordinate axis, that coordinate ordinary x and y, right. So, basically what we are doing is we are trying to bring a geometry given a quadratic curve. One is translate it, right. Once you have translated, then you can rotate it to look like a normal standard form of some conic or a quadratic curve, right. So, I am saying that geometry of this P is just that you are rotating points in the plane essentially, right. It is orthogonal transformation. So, we will see application, we will see exact example. So, how do you do that? That is the question, and that is the application of spectral theorem. So, what you do is the following. So, this given equation ax square plus 2 bx plus cy square equal to h, we rewrite in the matrix form. How do you write it in the matrix form? Imagine x and y are the variables. Imagine x and y are the variables. Then what is this? It is just this equation, row vector x y applied to the matrix with rows as a b and b c and the column vector x y. What is this product? This is precisely ax square plus bxy plus cy square, right, and that is equal to h. So, this is 1 cross 2, 2 cross 2, 2 cross 1. So, it will be a scalar and that is equal to h. So, this quadratic form is written in terms of matrices where x and y are treated as components of the vector x y. Now, advantage of writing this is, look at this matrix, this becomes a real symmetric matrix a b b c, it is a real symmetric matrix. So, once it is real symmetric, it will be diagonalizable by a orthogonal matrix. So, I will have a matrix P, say that P, this matrix P inverse is diagonal, and if I put that value here, you will see the new variables coming. So, of course, we are assuming that b square minus ac is not equal to 0 in the original one, then P, that matrix P inverse is equal to diagonal, that is a diagonal matrix. So, if I define, right. So, if I define x dash y dash as P x y, then what is that equation? P inverse is P transpose, again that is useful for real symmetric. So, I get x y P transpose d P, right, that is equal to A, right, this is equal to A. From here, what is this matrix? This matrix is, take P on the other side, P inverse on the other side, right. So, what is this matrix? That is equal to P transpose, because this will be P inverse here, P inverse is P transpose. So, P transpose D P, right. This matrix A B B C, this matrix, what is this? Multiply by P inverse on both sides. So, it is P inverse D P, right, but P inverse is P transpose. So, it is precisely P transpose D P, this is your matrix, and X Y was already there. So, that is equal to H. So, what is this thing now? X Y P transpose, it is P applied to X Y transpose, right, D P X Y equal to H. So, if I call this P of X Y as the new variable, that is what we have done, X dash Y dash. So, what is this equal to? So, this is precisely equal to X dash Y dash D X dash Y dash equal to H. What we have done is that 2 by 2 matrix, which came as a real symmetric matrix from the quadratic curve, we have taken the diagonalizable form of that and put that value, and that gives me a new variable. So, where D is the lambda 1, lambda 2 are the eigenvalues. So, this is the form that you get, right. So, what is the change of variable that I am doing? The change of variable we are doing is precisely given here, right, that matrix P applied to X Y gives you the new variables X dash and Y dash. Okay. So, first one was shifting the origin, right, that made all those other terms vanish, X, Y and those terms vanish, right. It became a canonical form. In the canonical form, now you rotate it, right, expressing that quadratic form matrix as a symmetric matrix, right. So, let us look at an example of this. Is it clear what we are doing, right? Basically, applying our spectral theorem for real symmetric matrices to visualize a general quadratic curve, right. How does it look like? So, it says to visualize it, first shift the origin, so that the terms X, Y and those terms vanish, it comes to canonical form, and then you rotate, you will get your standard form of a conic, which is easy to visualize. Okay. So, of course, in that, right, this delta is important, right, that should not be equal to 0. So, how does this delta characterize what kind of a curve I have got, right? It should not be 0. So, if it is positive, okay, so it depends on if it is positive, essentially it represents a ellipse, okay, and if it is negative, that essentially represents a hyperbola. So, those delta also characterizes what is going to be the shape of. So, that is not really important from this point of view, but that becomes important once one studies what is called differential geometry, right, where you study what are curves, what are surfaces, how do you characterize surfaces and so on, curves and surfaces. And so, this is essentially, and you can find out actually if there are two eigenvectors for this, right. So, let us say the first eigenvector is L1 M1, the second eigenvector is L2 M2. So, this your matrix P is going to be this, right, which is going to give you rotation, right. And what are these L1 M1? If you join L1 M1, that is what is going to give you one coordinate axis, and the other one is the joining L2 M2, because they are orthogonal, right. So, this gives you the new axis for when you shifted the origin, right, you get a new point, and when you rotate, right, you get the new axis. So, that point where you have shifted is essentially what is called the center of that curve, and these are the axes which are new axes. So, this theorem normally is also called the principal axis theorem. So, if you join L1 M1 with the origin, you get one line, L2 M2 you get another line, right, that is going to be the axis for the canonical form. Okay. So, let me just look at one example to illustrate this idea. Let us look at 4x square minus 4xy plus 7y square plus 12x plus 6y minus 9 equal to 0. What curve is this? We want to know. So, what are you going to do? First shift the origin, right, and then rotate it, right. So, anyway for delta for this, because A, B, C are not going to change when you shift or you do, right, they say as it is. So, you can find delta in the beginning itself is bigger than 0. So, it is going to be some kind of a ellipse by looking at A, B and C, right, and looking at delta which is A, B, B, C. You can see that this is going to look like a ellipse. So, first of all, what is the shift of origin? Where do we shift that origin to? So, I remember that equations E x naught plus that thing. So, these are the two equations. What is for shift of origin is given by, would like to know how these two equations come? That was shift of origin, right, putting x, shifting x to x tilde plus x 0 y 2 and making those other terms vanish, those two equations which came by putting those 0, right. So, these two give you, once you solve these two equations, because we already assumed that determinant is not equal to 0, unique solution will exist, and the unique solution is given by x 0 equal to 2 minus 2 and y 0 equal to minus 1. So, that is where the origin should be shifted to, okay, and that is what we call as the center of the curve, right. So, origin 0 0 0 should come to minus 2 and minus 1, and then I should rotate it now there. So, for the rotation, what is the canonical form of this? 4 x square minus 4 x y plus 7 y square, right, and once you change that, right, that comes out to be 24 equal to 0, okay, that h, right. So, that is, so what is the matrix for this now? This is A, this is 2b and that is equal to C, right. So, write down the matrix. So, that is a matrix. So, we want x y applied to this x y equal to 24, that is the form of the canonical form written as matrix multiplication. So, this is the matrix A. So, we want to find the corresponding matrix P which will diagonalize it now, because it is a real symmetric matrix, right, orthogonal matrix will exist. So, its eigenvalues are 8 and 3, one can check, I am not doing the computation here, but 2 by 2 is a quadratic, you can solve it, eigenvalues are 8 and 3 and these two are corresponding eigenvectors. Okay. Now, are they orthogonal? They are orthogonal, right, because for real symmetric distinct eigenvalues corresponding to distinct eigenvalues have to be. So, seems okay, fine, right. So, what will be your curve? What is the transformed curve? Lambda 1 x dash square plus lambda 2, right. So, that is your curve in the transform form, right, in the new variable x dash y dash, where what is x dash? That P, if you look at this matrix P, combine first row and second applied to x y is equal to x dash y dash, that is your new right, new variables. Is it okay? So, I just written directly, I have taken the last, see this is the form, transform form will be this, lambda 1 first eigenvalue, lambda 2 be the second eigenvalue equal to h. So, that once you write, so your equation comes out to be h was 24. So, this is your new form. Let us try to visualize it. Okay. So, what is this? This is the ellipse anyway, right. Clear, it is a ellipse, right. We are not finding eigenvectors because we are not really interested in finding, once we have formed a formula that x dash is nothing but p of x y, right, x dash y dash is p of that, right. So, you can do that and you will get this equation again is lambda of, because we have done it in the theorem, that computation, right. So, we are not really interested in p, we are interested in is what is the new equation looks like, right, as a part to visualize it. So, that is that original one, right, that is original quadratic curve. If I plot it as it is x y in the x y plane, what does it look like? This will look like this. Oh, I have to move it now slightly. this is what it looks like if I actually plot it. Okay. But if I is only after plotting it looks like an ellipse to us now, right. But if you do not plot it, we do not know what kind of a ellipse it is. So, shift the origin. So, let us shift the origin. If you shift the origin, so this will go here. So, this will become, this is a new shifting the origin, translation only, right. If you want to see how does this translation come about, but one can actually show that it is translating and kind of animated thing, no? Slowly it is going and translating. So, this is the one, and now what shall I do? I should rotate it by that matrix. So, here is the rotation, you rotate it. So, now it looks like perfectly nice ellipse I can recognize as we draw it kind of thing. So, that is how visualization is obtained. Okay. So, this is the final form, okay, and this is the, that was the axis, right, which we have original x axis, y axis have been transformed by that orthogonal transformation to this. That is what it looks like. You can try to do it, try to draw it, you will understand everything. There I am using a software called GeoGebra, which is freely available, free to download. Okay. I have just sat down and plotted all these things and rotated. All things are available here, how to translate, how to, right, everything is there. So, use that if you want to sort of have a change of scenario, that playing with software and trying to understand mathematics. Okay. So, that is an application of spectral theorem.